So this is where we kind of covered last week. So we have a general loss function, and then subject to the calibration condition, and then we use Lagrange multiplier, right? And then write it Lagrange multiplier to obtain the solution, which is 3, which is this form. Okay. And then plug in to the Lagrange multiplier and obtain a function, objective function of lambda. And then the profile loss function can be expressed as this. And this turns out to be related to a Legendre transformation of G, or conjugate, convex conjugate. And then final weight can be either inverse of the partial derivative of the original loss function G, or its partial derivative of the convex conjugate function. Okay, so that is the idea. And now the property, statistical property of the calibration estimator is that the thing is this guy is a function of lambda hat, and lambda hat solves lambda hat solves so the equation is right. So if you write, you define you had lambda as something like this, then the solution to lambda hat is basically a solution to this equation. And then we want to apply Taylor expansion. So if you think about how to do this kind of Taylor expansion, you first understand what is the limit, right? But let's assume that limit exists. So say that limit is lambda star, and then we want to do partial derivative, Taylor expansion, and something like that, right? So this is where you would end up if you apply Taylor expansion. And then the problem is that you can, this is known, right? You can compute it, but this is, you don't know. So what to do? And so idea is you can also apply Taylor expansion over this one. To take the Taylor expansion of this one with respect to lambda star. Okay. Plus times, oops. Then you can get, so if you do Taylor expansion, you will get lambda star plus right, lambda star times lambda hat minus lambda star, right? So this is basically is approximately equal to 0. So that means you can write your lambda hat minus lambda star to be the inverse of this guy, right? Inverse. And then you had lambda star. Oh, should I should write a same color. You had lambda star. Okay, so this is approximation. And then idea is you use this one and then plug in here. Okay. So then you can get something like plus. So this, I mean the actually you can take expectation too. So some constant times you had lambda star. And this constant is indeed expectation of lambda minus inverse of the so that is the classical way of obtaining tail expansion of this kind of estimator. So you have an estimator, but you realize that your estimator contains some nuisance parameter that creates some difficulty in computing the computing the asymptotic properties. So you need to so if you expand it, then this is actually a so then this guy can be written as some kind of a linear function, summation of the uh, uh, some kind of eta I. So eta I is a function of uh, xi, yi, ti. So then it becomes a kind of linearized, and this guy is sometimes called the influence function. But we don't have to know all these terminology. But the point is how to do tail expansion. So so this is more like a classical theory, but here's a more step-by-step approach. So first thing is to figure out what would be the limit of lambda hat. So what is the limit of the lambda hat? So let's lambda star be a private limit of the lambda hat. What is the limit? And the idea is that we know that u lambda hat is to 0. We know this. And we know that also we know that what is the if I know so first step is lambda hat is this by the definition of lambda hat, right? Lambda hat is satisfying this equation. Second is what is this one? So what do you mean by that? Well, let's write what is u hat, by the way. So u hat lambda is an equation that determines the lambda, right? So that is the in our specific case, this is omega I lambda, right? And then this is what yi, no xi minus x bar n. Let me see. Right, this one. So which is this one? So this is our estimating function for lambda. And then solving this equation will lead lambda hat. and so then we now let's second step is what is the lambda hat? I mean you had lambda for given lambda. So lambda is constant just for any constant, right? For given or given lambda. What is this? Okay. And so that is then the expectation here is expectation with respect to t. So the expectation is actually with respect to given conditional expectation. So that is right. So TI is on the we are talking about CRE. So this is and so lambda star, the probability limit should satisfy probability limit because by the continuity, right? I mean uniform convergence, and because we know that you had lambda will converge to this, converge to its expectation. So then the solution should converge. The solution to this equation should converge to the solution to the limiting equation. Okay. Although we need to be more rigorous, we need the uniform convergence. So uniform in lambda, but let's forget about the details. We are just doing more love derivation here. So so anyway, this is a function of. By the way, this is ui lambda is actually G inverse lambda 0 plus lambda 1 x prime x1 I. So for this to be 0, right? So for this to equation to 0, that means we need this one equal to 1 over and 1. Right? So this in the limit. Okay. So I guess my point is that we don't know the value of lambda star per se, but lambda star should satisfy this in order to make this one to be equal. So that means one choice is lambda 1 equal to, so lambda, so that means it cannot really depend on xi. So and then if you the inverse exists 1-to-1, and then so I so I guess I put a lambda 1 star equal to 0, but that is not really important. What is important is we just, no matter which choice of lambda star, the answer is this. As long as so this one, as long as this one, so that's the only condition in some sense. Okay. So this is not really accurate. We don't need this, right? We don't, This is just one way. Uh, yeah, right. So we don't. Well, later we need more, a little bit more, but okay. But this is just so just to give you a flavor of what lambda star would be. So what condition the lambda star should satisfy? Should satisfy this. Okay, so let's move on. So point is, suppose lambda star exists, right? So if it exists, it should satisfy this. Let's see. Okay. Now, here's some interesting technique. So the technique here is to avoid this tedious Taylor expansion. So I want to do something, some technique. This is kind of my tip for deriving linearization of this kind of problem. This kind of problem. So idea is, okay, I know this is zero, right? I know this is zero. So that I can multiply anything and add, right? So then this is zero anyway. And then write it as a function of lambda and beta. And then I want to somehow transfer the randomness of lambda hat to the randomness of beta hat. So I want to, because to the linearization, I want to get rid of the randomness, right? And the sampling variability of lambda hat. And so how to do that? Well, okay. So idea is, if you think about doing Taylor's expansion of this guy, so suppose you do Taylor expansion, then you will do something like this, right? Something like this. You have augmented index. You have augmented index beta here, but you can still do Taylor expansion, right? Okay, so this is your Taylor expansion. But so question is, we can always take expectation in the partial derivative, and then question is, under what conditions can we ignore? Can we have these two equivalence? Okay. I mean, can we ignore this the first order linearization term? Well, that is true only when this is zero, right? So this, if this is zero, well, negligible, then we don't have to do Taylor expansion. Okay, so that means so, but this is not equal to zero in general. In general, it's not equal to zero. But on some particular, on some value of beta, we could achieve this. So that is basically the idea. So if we can find beta, okay. So if we can find beta star such that this one is zero at this beta star, then the effect of estimating lambda, so the sampling variability of lambda hat can be ignored, can be safely ignored. So so basically, beta star is the solution to this. Beta star is the solution to this. Then you can basically, so here's a logic, right? I mean, originally you are interested in this. originally this is what you are interested in doing Taylor expansion. But you create an augmented index, right? So you make so you have actually double index, which is more like lambda plus u beta, no, u lambda, right? So this is a calibration. You had lambda and then beta. So this is your augmented one. Okay. And then it satisfies two properties. First property is at lambda equal lambda hat. Beta hat calibration beta equal to beta hat lambda. Right? At lambda equal lambda hat. Lambda u, the second term is 0. So you can get equivalence. So that means you can get this one. Secondly, at beta equal beta star. Then what? Where beta star satisfies the Randall's equation 10. Then lambda's hat is approximately equal to then this which serves the Taylor expansion. So this one already linearized. This so all you have to do is to find, so basically but this one is theta hat by 1, right? By 1. So by 1, you have this equivalent, right? By 1, you have this equivalent. By 2, you have this equivalent. So that means you have this equivalent, which is the Taylor expansion, right? So this equivalence, so this equivalence is actually a Taylor expansion of theta hat cal lambda hat. This is because this is what you're interested in the beginning, right? This is what you're interested in the beginning, but we kind of augmented, construct this estimator intentionally. Okay, and just to try to find the best, choose a beta star that makes make the takes the role of the linearization. Okay. So because of this logic, right? Using this logic, we are able to obtain this one, the first equation. And second equality comes from the property of the what? This is 1 over n, right? N1. Because I already here, this one. So this is the minimum condition for lambda star. So we know that. So then means we get this one. So actually, to be more clear, we don't need this one. Okay. So this is what we are interested in, right? The calibration estimator is equal to this. So that's basically the result of Taylor expansion already, right? The only thing left is what exactly is the form is. What is the form of beta star? That is the only thing left to be solved. So that is basically equation. We need to solve 10, equation 10, right? So what is so let's write out the equation 10, the component in equation 10, which is this guy. So equation 10 is this guy. So we need to write down what is this. So by the way, this is the weight, right? This is the WI hat lambda. So we and then apply it to stuff. Okay. By the way, what is what is this guy? Well, this guy is here, right? Here. So this is constant with respect to lambda. So you don't have to worry about because we want to compute the partial derivative. We want to evaluate equation 10. So that means we want to evaluate the partial derivative with respect to lambda, right? So that means this part it goes away. So that's why you get this one. And but we already know this guy is this guy itself is 1 over n. N1, right? So that means because this one does not depends on individual values. So this one, so let's say that this one is it doesn't depend on I. So it can be something. Let's call it C, constant C. So basically the C cancels and beta star it becomes you just solve this. The expectation of this guy. So the expectation here is expectation with respect to T1, Ti. So the expected value of Ti is just another constant. So you get this, which is actually the regression coefficient, right? So that means the calibration estimator is asymptotically equivalent to the regression estimator. Okay. That's the basically the all for chapter week 7 lecture.